We can study.
Yeah, well, are we?
No, we can try.
Okay, I think I'm going to start just a minute or two early here because I just want to talk about the test a little bit. And before I start discussing it, I wanted to explain something to you, just in case you don't know. Of course, when you take the average, all you do is, add up all the test scores, right? And then divide by the number of tests that were taken, right? That's how we do averages. So I'm going to assume everyone here is happy with averages. But there's this other thing called the standard deviation, which, unless you've taken a statistics course, a lot of people don't understand what standard deviation is. So what I'm going to do is I'm going to give you an example, and it should help you understand standard deviation. So let's just imagine that I had two students in a class, all right? And I give a test, and one of the students gets a 0 and the other student gets 100, right? Then what would the class average be? 50, right? So the average would be a 50. You add them up, divide by 2. So, all right, what about this? What if I give a test, I have the first student gets a 25, the second student gets a 75. What's the average? Still 50, right? And what if they both get 50s? Your average is still 50, right? So the average, although it does tell you something, it doesn't tell you what I think is the most important thing, and that is, are these students at the same place or are they at different places? And of course with this, we have one student who really gets it and one student who doesn't get it at all. Here it's a little better, and then here, even though it's a 50, they're both right there together, right? So the measurement of how far away the scores are from the average. So if the average is 50, these scores are pretty far away from 50, aren't they? These scores are closer to 50, and these scores are right there. So this right here, you would have a very small, in fact it would be 0 here, but this is a small deviation, and then this right here is a large deviation. Make sense? So now I'm going to show you the data for the class, all right? And I'll talk about the standard deviation once we get to it. All right, so for this class, on the first test, I was extremely pleased, all right? We had 23 students take the test. We had a class average of an 80.6, which already right there is high. Normally my class averages are right around 74, 75 for a Cal 1 class. So I don't see 80, 81 as an average very often. So that's good. But more importantly, the standard deviation is 13.2. I'm used to seeing 18 or 19. And it may not seem that big of a deal, like 18 is maybe 5 points more, but that's an entire half letter grade, 5 points. And so what this is saying is that the class is pretty much within everyone lies within about 13 points of that 80. So, like up to a 93 and down to like what? 67-ish, right? But everyone's close together as opposed to spread out. And that is good. All right? I'm happy to see that. Because it's very difficult when you have a class full of students who get it and students who don't get it, and then you're trying to find that middle ground to teach to. Looks like everyone in here is pretty much together. Does that make sense? Okay, so I know this, I just went crazy with my chart here. So this is the scores on the test from the highest to the lowest. And you can see the highest grade in the class was a 102, lowest was a 52.7. We had 5 A's, 10 B's, 4 C's, 1 D, 3 F's. Okay? Now, here's your average line right here. So the students that were above average are over here. Students that were below average is down over here. And then I have them broken up into percentiles, or sometimes they're called quartiles. And the difference is like 50th percentile is not the same as your average. 50th percentile means that at this point right here, half the students are above it and half the students are below it. If you're in the 75th percentile, then if you're over here, then you're in the top 25% of the class. If you're somewhere over here, you're in the bottom 75%. Then here's the 25th percentile. I don't know why I made that dotted. Oh well. No, 75th, 50th, average. Sorry, I think that's supposed to be, sorry, this 25th percentile is supposed to be the red. This dotted one is passing. So, all right, make sense? So overall, very pleased. I'm cautiously optimistic that we are headed in the right direction. Now, for those students who may have struggled on this test, I don't normally do this, but I want to require anyone here to come see me at some point. Just make an appointment, kind of like what I was offering earlier in the semester. If you absolutely do not want to come see me, I can't force you to come see me, but I'm strongly encouraging you to come see me, because what I want to do is just go through the test with you. I want to see what went wrong, see how we can adjust things to help you do better on the next exam. It's only one exam. I mean, it's not the end of the world if you didn't do great on it, you know. On the other side, it's one exam. So even if you did well, it's still just one exam. So you have plenty of room to improve, and you have plenty of room to still screw it up. So, you know, it's only one exam. So keep your foot on the gas pedal. I hope that you felt that the test was fair. There was one question on the exam, and just so you know how I graded this, there were 12 problems, and I usually grade every test as if each problem is worth 10 points, because it's just easy for me to grade out of 10 on every problem. So the most you could have got was 120 points. Does that make sense? If you got 120 out of 120, you would have got 100 on the test. But then I decided to throw out number 7 because it was, I don't know, I guess it was the first test, so I was like, all right. I told them nothing continuity would be there, but then I gave them a question on continuity. But it really wasn't a question on continuity. It was more of, well, it was, but that was just to show you that, look, on every test, I like to pick at least one problem that is more theory than it is computational. And so number 7, I counted as a bonus. If you got all 3 of them right, I think I did +3. Okay?
What were they?
What are the different types of discontinuities? Jumps, holes, and vertical asymptotes. Anywhere you have vertical asymptote, you're going to have a discontinuity. Anywhere your graph breaks and has a jump, or anywhere you have a hole in the graph. What else? Tests are over there on that table if you want to grab yours. Okay. What else? Anything else I want to talk about? Yeah, so really there were 111 points possible. 110. There were 110 points possible because it was really graded out of 11 problems worth 10 each. Okay? So that's how, and then some of you got a bonus for not using a formula sheet. On this test, you had to know the formula for the derivative, right? Like you had to know limit h goes to 0. That you had to have up here. So if you're like me, I was not very good at memorizing formulas as a student. So what I did is I would just come to the exam and I could memorize it for about 5 minutes and then my brain would lose it, right? So what I would do is I'd memorize it, and as soon as the test started, I would write the formula down on the test. And you're completely free to do that, all right? But just, you should know going into the test, having practiced and done your homework, you should know what formulas you need to know. Like everyone should have known they needed to know that limit h goes to 0, f of a plus h. Because if you didn't know that formula, you couldn't do the last 2. And then you're in trouble, because that's already 20 points gone. All right, any questions, comments, concerns, anything you want to talk about in terms of the exam? We're going to put it to rest.
Exam 2?
What's that?
Exam 2?
Oh, exam 2 is right around the corner. Exam 2, here, it doesn't make a lot of sense that exam 2 is like on the 19th of, no, sorry, 19th was already in the past, is on the 7th of March, which is, let's see, 1, 2, 3, 4, we have 4 class meetings, then we have our next exam. All right, now the reason for that, there is a reason, is that I'm actually going out of town on the 6th, and so I decided to make it easy for a proctor to get someone in here. Instead of having some substitute come in here and lecture to you, I'm going to just do an exam on that day, and it's easy to get someone in here and just pass out exams. Because anytime I've ever had a sub, I always have to come in that next class and redo it anyway because, you know, it's presented a different way and people are confused. So our exam will be on the 7th, and it will cover 2.2, 2.3, 2.4, 2.5, but not 2.6, I don't think. We'll talk about it. I'll show you 2.6. I don't think you'll want to have an exam on 2.6 2 days later. You know what I'm saying? Because 2.6 we're covering on a Tuesday, your exam would be on a Thursday. That only gives you, 48 hours or so. So I'm thinking we're just going to go 2.2 through 2.5 for that exam. And there's plenty of information there. All right, there's plenty of material to put on an exam. Does that answer your question? Okay. All right, let's get going. So, the main idea that we have right now, all right, the main idea is that if we're given a function, right, y equals f of x, if we're given that, then we can calculate this thing. Now I'm referring to 2.2 now, because 2.2, remember, was not on the test, but we did do 2.2. So we said that we could compute this new thing right here, which we call the what? What is this thing called? Okay, we say f prime. That's one thing we call it. What's something else I could call it? The derivative of f, right? Okay, so the derivative of f. And geometrically, this thing represents the slope of the tangent line at x. So in 2.2, we switched the a that was in here over to an x. That's what we did in 2.2. We said, hey, a could be anything, let's call it x. And then we discovered that, okay, well, if we start with the function, take its derivative, we get a new function. So we start with a function, f of x, take its derivative, I'll just say derive. We derive it, take its derivative, and we get this new function, f prime of x. Okay, start with the function, end with the function. These two functions aren't the same functions, right? Now, to do this, to derive or take the derivative, we have to know a formula, and the formula is this: limit h goes to 0, f of x plus h minus f of x all over h. And that's the formula that we use to do the homework in 2.2. And in 2.2, they give you a bunch of functions, and then you calculate this. So I'm going to start right now by doing one example from 2.2, and then we are moving on to 2.3, all right? So I just want to, because it's been an entire test since we've talked about this. So let's do an example, specific example. Let's see. Just make one up here. Well, let's see what the book has for us. Cold beer? I did that to my daughter the other day. I opened up a Sprite for her and said cold beer, and she's like, Daddy. All right. Okay, this one looks interesting. How about this? How about y equals x to the 3 halves? So just so that we know what the heck raising something to the 3 halves means, let's just remember that when you have x, well, let me do it this way. If I have x to a fractional power, like this, what that really means is that you're taking the mth root of x to the nth power. So this means this. This is back from college algebra. So this we called rational exponents because your exponent is a ratio, rational exponents. This is called radical notation. These are two different notations that mean exactly the same thing. So when you see that over there, that really means what? Square root of x cubed. Now I don't need to write the 2 out here because the square root implies it's a 2 out there, right? That's just so we all understand that that's the function we're looking at. Now I need to find, I want us to find right now y prime. So that means I want us to take the derivative, right? Yes? So to do this, I need to do the limit as h goes to 0 of f of x plus h minus f of x all over h, right? Like that. That's what I need to do. Now, up here, I define this thing y equals this, right? I don't have f. You have to understand that this y is really the function of x, right? Y is a function of x. So let's see how this works out. We take the limit, h is going to 0. All right, f of x plus h means I'm going to plug x plus h in there, right? Into that for x. So what would that be? X plus h, all raised to the 3/2, right? And then subtract from that what? F of x, which is itself, and then all of this divided by h. Right? That's where we are. Now we have to figure out what this is, right? What in the world does this become? We should already know that if we let h go to 0 here, if that's 0, then these two things match, don't they? And then we get 0 on top and 0 on the bottom, which we knew was going to happen to begin the problem anyway. So we need to somehow get this h to somehow cancel. And this might be somewhat difficult to do. We could look at a conjugate. I don't think it's off the table. Let's convert this over to radical notation. Might be easier to work with. Okay? Oh yeah, also hold on before you say, notice how I keep writing the limit each time. Right? So on your exams, I did take off for that. And it's not because I'm really anal, because I'm not that anal. I think I'm a pretty relaxed grader, but really it's like leaving periods off sentences. It's even more than that because, I mean, without the limit, it's just algebra. It's the limit that makes it calculus. So you need it in your expressions. So if I rewrite this first one, it's the square root of x plus h cubed minus the square root of x cubed all over h.
Now, before you take the conjugate, could you also do square root of x plus h and then write it all out the 3 times and then did you FOIL it?
I see what you're saying. Like expand that, do x plus h times x plus h like 3 times.
FOIL it within the square root?
Sure, you could do it as long as it all stays under the root. You could do that. I think maybe we'll try the conjugate. Yeah, let's just try it. Let's see what happens. Gonna hope for the best. Okay, equals the limit as h goes to 0. All right, so I'm going to do square root of x plus h cubed minus the square root of x cubed all over h. But I'm now multiplying it by the conjugate. So I'll do a different color because I'm introducing something now, right? A 1 here. And my conjugate is everything I see there. What's the only difference? Plus. And then whatever I do on the top, I must do on the bottom. Okay, here we go. So now, this will equal, let's take a look at that numerator. Still have a limit. All right, so when I multiply the numerator out, it looks bad, but it's not that bad. Here to here, right? What do we get? just x plus h cubed, because the roots go away. And then the denominator, I'm sorry, I don't know why I said denominator. The middle pieces cancel, right? The middle pieces will cancel. And so all you have to concern yourself with is the last ones, these two, which should be negative, right? And negative what? Just, so the roots are going to go away, right? Because you're doing root times root. That means the root goes away. You get x cubed, just what was underneath it. And now on the bottom, I'm not going to move this h. I'm not going to try and multiply the h through. I'm just going to put h, and then in parentheses, I'm going to put the conjugate down here. And I've told you several times, don't try and pass don't try and simplify the denominator, because ultimately you're trying to get that h to cancel, right? So just leave it out here alone. Just make sure you put this in parentheses. So we all good there? All right, that doesn't look very good as far as like, I don't see an h can cancel. Please don't tell me this h cancels, right? That doesn't happen. But maybe there's a way we can free this up. Maybe we can free up an h from here. So let's cube that. Let's cube it. That means we have to do some algebra over here. So on the side here, little scratch work, do x plus h times x plus h times x plus h again. That is not x cubed plus h cubed, right? Okay, you have to actually FOIL this all out. So the way I like to do this when I have three of these, I leave the first one alone, and I expand these two out. So if I multiply, I'm going to trust that you could do that, right? Multiply it out, collect like terms, you would get x squared plus 2xh plus h squared. And then you have to multiply this times this, so you go here, 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 here. So 6 multiplications. X cubed. I'm so happy to see x cubed. Why am I so happy to see x cubed? Because this x cubed back here is going to kill it, right? Okay. So I have x cubed. I have plus, what, 2? So x squared h. And then plus xh squared plus hx squared. And finally, h cubed. Okay, so that's what I get when I multiply those out. Collect like terms. I have some like terms, don't I? Yeah. This and this are like terms, right? I have 2 of them and then 1 of them. Doesn't matter that the order is flipped here, right? That doesn't matter? Because multiplication doesn't matter. Okay, so I have 3 of those, don't I? And then this guy right here is the same as this guy right here. So I have 3 of those. Okay, so I have x cubed plus 3x squared h plus 3xh squared plus h cubed. Yeah, well, yeah, let's come back here now. Okay, so I'm going to come back to this now. This equals limit h goes to 0. Notice I didn't have a limit over here, right? Because I was just doing some scratch work on the side. This is algebra. I'm just going to go do that on the side. I'm going to come back over here. Here's my limit. Now I just plug all that stuff in. X cubed plus 3x squared h, squared h plus 3xh squared plus h cubed, then minus x cubed, right? That's our next piece. And then all of this over h, and then that conjugate. My goodness. I don't make this stuff up. Here we go. X cubes are gone. Really happy to see that, because everything that's left has an h in it. And if everything that's left has an h in it, I can factor an h out and then cancel the h and then let h go to 0. So my next step is to go ahead and factor the h out. Limit's still here. All right, let's pull an h out. So I'll have h comes out 3x squared plus, pull an h out of this one, 3xh, right? Pull an h out of that one, h squared. Right, so I've pulled h from here, here, and here. And I still have this over my h that was there. It's going to cancel. And then my conjugate. h's are gone. I should no longer have division by 0. So at this point, we let h go to 0. And so I'm going to stop writing the limit. And I'm going to say that this equals, let's see, 3x squared, gone, gone, right? So 3x squared over, now be careful here, if h goes to 0, then this is just x cubed, right? So you have the square root of x cubed plus the square root of x cubed again, which is 2 of them. 2 square roots of x cubed. Yeah, 2 of them. Make sense? All right. Now you could say you're done right now because that is an answer. And our answer should have x in it. Remember, we started with a function, we took its derivative, we should have a new function. There it is. But we can clean that up a little bit more. We can use property of exponents like this. Remember, if you have x to a power over x to another power, this is x to the n minus m. You subtract the powers. So first let me rewrite this. This is 3x squared over 2x to what power? Is it 2/3 or 3 over 2? It's 3 over 2. Right, so I'm just taking this expression back to rational exponents. So it's this. And now I have a power on top, power on the bottom. And so my answer is this fraction, 3 over 2, and then x raised to the 2 minus 3 halves. So you have to subtract those, so you have to get a common denominator. Right? 2 minus 3 halves would be the same as 4 over 2 minus 3 halves. Right? Get a common denominator. That's like 2 over 1. So what would that be? 3 halves x to the what? 1/2. Bam. Okay, so yeah, if you don't like that, you could just, that's what that is, right? There you go. Woo. So the derivative of x to the 3 halves is 3 halves x to the 1/2, or 3 halves times square root of x, yes?
So if you left it at the 3x squared over 2x, 3 half, no, one past that. If you left it at that, would that technically be correct then?
I mean, technically it is correct. Technically it is, yes.
Is that like rationalizing where later we find out and we use this?
No, it's just like, to me, if you leave it like this, to me, that's like you leaving this and not telling me that's 7. You know what I'm saying? Like, to us in calculus, from here to there should not be a huge leap. It should be like doing this. Is that fair? It's not wrong. I mean, I can't say it's wrong. It's just, yeah, that's 7. Yeah. Yeah, it's aesthetically unpleasing. And then think about this. What if now you're asked to find the second derivative? Right? You wouldn't want to work with that, right? You'd rather work with this or that, right? It's just, this would be easier to work with. Okay. So I guess after you do all the homework for 2.2, which I'm sure you've all done, you will have suffered appropriately with the limit. And then we get to 2.3. So we're moving on. So what we're going to get now are some formulas. And I promised that these would come. Remember, I told you that there would be a lot of suffering with the limit. And then at some point we would give you formulas that would be shortcuts. And then you'd be super happy, at least for like a day. All right, so we now established some shortcut formulas which will allow us to compute derivatives without having to use the limit. We can do a derivative and we don't even have to write limit down anymore. It's just going to be a formula. This will make our lives drastically easier. However, once we get comfortable with these formulas, we'll be tackling some much more complicated functions. So I told you this already, that once you get the formulas, then we crank up the level of the functions. So here we go. First formula. The derivative of a constant is 0. All right? You no longer ever need to think about this. If anyone asks you to take the derivative of a number by itself, the answer is 0. So let's try and understand what this is saying. First of all, d over dx means take the derivative, all right? Take the derivative of a constant, and I'm telling you the answer is 0. Let's see if we can convince ourselves of this without any sort of proof other than visual proof. Here's an example. I'm going to define a function y equals, somebody give me a constant. 4, okay? I heard 4, yes? Okay, so if I asked you to graph that, what would it look like? A line? What kind of line? Straight line, yes. Horizontal line. 1, 2, 3, 4. We go up 4 units, right? We would draw a line like this. So the derivative of this function is the slope of the tangent line, right, at different points. Well, go pick any point you want on this line and tell me what the slope of the tangent line has to be. So the tangent line would have to be like this, right? Flat. And what's the slope of a flat line? 0. And it wouldn't matter where you are. You could pick any point, right? Any point you want. The slope of the tangent line at that point is always 0. Make sense? So does it make sense that the derivative is always 0? Done. Okay, so we don't have to worry about that. If we ever see a constant and we need to take its derivative, then the answer is 0. No work. See, already, isn't it great? All right, how about this one? The derivative of x is 1. If you ever see x by itself, x to the first power, right? X is x to the first power. The derivative is 1. So let's try and verify this visually first. What is the function here? Y equals what? X, right? That's what I'm telling you. That's the function. So if I ask you to graph this, what does that look like? The diagonal line. It's the perfect diagonal line, isn't it? It's the one that goes through the origin, has that perfect slope of what? What's the slope of this line? 1, isn't it? Isn't the slope of that line 1? Tests are on that table. The slope of that line is 1. And so if you pick a point on this line and ask me what the slope of the tangent line is, well, it's going to be the same as the slope of the line itself, which is 1. Does that convince you? Are you convinced? Okay, now I'm going to convince you a different way, because I'm not going to be able to convince you with pictures the whole time here. So let me show you how I do this, proving it. I'm going to prove this using the limit. So remember, y is x, right? Now, we'll call that f of x. So what is the derivative of this using what we know about the limit? It's limit, h goes to 0, right? And then f of x plus h minus f of x all over h. That's the formula, right? Now, what is f of x plus h? What would happen if you take x plus h and plug it into that function? What do you get? Just x plus h, right? So you get x plus h, and then minus, what's f of x? X, okay, over what? H, and what happens here? X's cancel, and then the h's cancel. And when you do the h's canceling, you get 1, don't you? So you have h over h after the x's are gone. These cancel. This means limit h goes to 0, but now that's a 1. And we have already seen that the limit of a constant is just the constant. So this is 1. So this is a visual proof that the derivative of x is 1. And this is a calculus algebraic proof that the derivative of x is 1. Understand? All you need to remember now is that the derivative of x is 1. All right. Now we're going to go after something a little harder. The almighty power rule. I'm not sure I could make it any more clear. I mean, have I told you I wish I could do a cartwheel? Have I said that to y'all yet in here? No? I've never been able to do a cartwheel. But I wish I could, because if I could do a cartwheel, there are certain times in the class where I would do a cartwheel just so you'd remember how important this is, all right? So imagine a cartwheel right now. This rule is never going to leave you. Into engineering, wherever you go doing math, the power rule is one of the fundamental rules for taking derivatives. So let's take a look at what it's saying first. And I showed you this rule before. This is the way we take the derivative of x to any power at all right? So let me give you a specific example. Y equals x to the, I don't know, how about 3/2? We just did that, didn't we? Now we know what kind of work that took, right, to do it with the limit. But this rule says that if we want to take the derivative of this, all we have to do, and I'll put the rule down here, all we have to do is take the n that's out here, bring it out front. See that? And then subtract 1 from the power. And you're done. So let's try it. The derivative of this, y prime, should be, so the power is what? What's n for us here? 3 over 2, right? So that's going to come out front, 3 over 2. X to the n minus 1, so 3 over 2 minus 1, which is 3 over 2 x to the 1/2. Well, crap, that's what just took us like 10 minutes a second ago, right? A little while ago, it took us like 10 minutes to do that. Isn't that nice? Okay, now, it would not be right of me to give you that rule without proving it to you. So I'm going to prove the power rule to you now, all right? It's going to take me a little while. At the end of the day, the proof doesn't matter in terms of you're not going to be tested on it. I'm not telling you to like turn me off and check back in later. I want you to see what it takes to show something like this. All right, so here we go. Let's just start, let's just say y is x to some power, right? And let's call this f of x. And let's try using our definition of the derivative to do this. And we're going to quickly see how bad this is going to be. So we're going to use the definition. This is the definition. Have y'all ever seen Kill Bill? I'm not sure which one it is, but the one where she's training up in the mountains with Pai Mei. Is it Pai Mei? If you haven't seen Kill Bill, don't worry about it. Who's seen Kill Bill? Maybe I should make sure that enough of you have seen it. Okay. So she's up in the mountains, she's training, right? And like there's a scene where she's sleeping, but like she wakes up and she's like punching in her sleep because that's all she's been doing is training, right? I want you to wake up in the middle of the night and like like mumbling, limit h goes to 0, f of x plus h minus x. No? Is that too much to ask? This should be like burned into your head at this point. All right, so here we go. Limit h goes to 0. All right, when I plug x plus h into that, what do I get? X plus h to the n, right? And then minus what? X to the n, and then all of this over h. And this is where I run into the problem. Because I don't know what n is, do I? Like if n was 3, like in the problem we did a little while ago, n was 3, we expanded it out. But see, n is not given to me here, right? So I'm not quite sure what that looks like, unless someone tells me what n is, right? But if I'm trying to come up with a formula, I have to leave it as n. I'm not allowed to switch it to 3 or something. So, what is this? All right, so here we go. We're going to put this on pause, all right? I'm going to come back to it. Remember, our goal right now is I need to figure out what that is, all right? So let me see if I can show you what it is. Let's think about some powers of x plus h. So we all know that if you take x plus h and raise it to the first power, you just get what? X plus h. Now I'm going to write this right here in the middle, leaving myself some room. Okay? Way over here. Just bear with me. What would this squared be? So there you'd have to FOIL them out, right? And I'm going to trust that you could get this. If you were given enough time, you could expand that out, right? And you would get that. Now, to the third power, we just did the third power, didn't we? So we have that written down in our notes, so we'll just cheat and we'll go back there and look. We'll see it's x cubed plus 3x squared h plus 3xh squared plus h cubed. All right, that's what it is. Let's do another one. X plus h to the fourth. Any guess as to what the first one would be? X to the fourth, seem reasonable? It is, okay. So there's a lot of work that would have to happen here, right? And I'm not showing it. Any guess as to what the next one would be? 4x cubed h? That's a really good guess. Where'd you get that from? There's what?
Pattern.
There's a pattern. Where's the pattern?
Starting from the top, going to the bottom.
So look at, I've almost created like a triangle here. Do y'all see this? Do you notice that the first term is always x to some power, and the power on it is actually that power. So this is squared, that's squared, cubed, cubed, fourth, fourth. So the next one should be fifth, x to fifth, sixth, seventh, right? So that seems reasonable. But what about here? What's the pattern here? Yeah, I have to do something to this one because we're looking at the second term, right? Second term, second term, second term. Let me go up here and look at this. This is a 1 right here, right? I don't have an x there, do I? Well, I actually do. It's x to the 0, isn't it? So look what happens. This 1 matches with that 1, right? This 2 matches with that 2. This 3 matches with that 3. This 4 matches with that 4. Okay? And then, what about the x's? No x's, 1x, 2x's, 3x's, right? How about h's? They all have h, 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 h. Do y'all kind of see that pattern? I'm going to show you the pattern in a better, like more detailed way in a second, but any idea what the next term would be? Most students don't get this one. 6x squared h squared. Now, I don't expect for you to know if you've never seen this before. And then the next term, you're just going to have to take me on faith here. Anyone know the next term? 4xh cubed, and then what about the last term? H to the fourth. Okay, I'm going to do one more of these. And then I'm going to show you like something I think pretty cool. So we know this one should be x to the fifth, right? Plus, and then what about the number in front? 5. And then x, this power should come up, so 4, and then the h stays h, right? But what about the next term? 10. Yeah, 10x cubed h squared. And then the next term? 10 again. If you're sitting there going, what the hell's going on? Just hang tight, okay? And then the next one is 5. 5x to the fourth, and then the final one is h to the fifth. Now, if you were to multiply these out 5 times and do all that, you will come up with this, all right? So someone was trying to figure out if there was like a formula for this, and they noticed a pattern in here. All right, so I'm going to illustrate the pattern. I think once you see it, it'll be pretty cool. I need one more thing. We didn't put up here what's x plus h to the 0 power. So what's anything to the 0? 1. So I'm put a 1 right there. All right? Y'all got this? Okay, watch this. I'm going to go through here with my red marker, and I'm just going to put every coefficient, I'm going to do it in red. So this is a coefficient 1. The coefficient in front of here is 1, and then this one is 1, right? And then the coefficient here is 1, and then this coefficient is 2, and this coefficient is 1, yes? And the next one is 1, and then 3, and then 3 again, and then 1. And then we have 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, and 1, right? You'll see that?
So the pattern is that the first two will count where you add up the first two to get your second, and then you add up that to your third to get your continuous, if that makes sense. Like, for example, if we use the third line, I guess the second to the fourth line, x plus h cubed, you're adding 1 plus 3 to get 4, and then 3 plus 3 to get 6, and then 3 plus 1 to get 4, and then at the bottom you're
Exactly. Hold on. Yes, that's exactly what's happening. So this right here, I've created this thing which is called Pascal's triangle. Now, Pascal was a mathematician. He gets credit for this triangle, although the Chinese had it hundreds of years before Pascal had it, okay? So he shouldn't get credit, but it's called Pascal's triangle. So the pattern here is that you're going to draw a triangle, so each row gets one more number each time. Your ends always have to be ones, okay? And the way so you start at the top, you have to have one number, right? And your ends have to be one, so the only thing you put there is 1. The next row, your ends have to be 2. Have to be 1, so you only have one choice, right? 1 and 1. The next row, 1 and 1 on the ends, and then this number comes from adding those two up. So I get 1 plus 1 is 2. Next row, the ends are 1s. How did I get 3? 1 and 2 added. How did I get 3 here? 2 and 1 added. Next row, 1, 1. How do I get 4? 1 and 3. 3 and 3 is 6. 3 and 1 is 4. Does that make sense? So the next one here, that's where our 5 comes from. That's why we get 10 twice, right? 4 and 6, but then 6 and 4, and then 4 and 1, and then you're 1. What's that? Pyramid scheme? Yeah. So this is the pattern that gives us our coefficients. But what about the powers on the variables? There's a pattern in the powers. So let's just look at this last row because I think it'll be the easiest to see. Forget the numbers. Forget the red. Just look at the x's. We start out, look at the variables. We start out with x to the 5th, right? Which is this. Now, when we move to the next one, what happens? The power on x goes down, and the power on h comes up to h to the first power. On the next one, the power of x does what? Goes down, but the power of h goes up. And then the next one, power of x came down, power of h came up. Next one, power of x goes down, power of h comes up. Understand? So let's see if we can do the next one. What would x plus h to the 6th be? So we know it's going to be x to the 6th, right? We know that because they're all following that pattern. Plus, now what about the number? So we're 1 and 1 on the ends. Here and here, 6, right? So this next one is 6. What about the power, the x? X to the 5th. What about h? Just h, right? Plus, what's the next coefficient? 15. 15, x to what? 4th. And then h squared. Plus, what's the next coefficient? 20. X to the 3rd, h cubed, okay? Next one, 15, x squared, h to the 4th. 2 more. Where am I at? Right here, 6. So plus 6, x, h to the 5th. So x came down, h went up. And then the final one is plus 1. You don't need the 1 in front of it, h to the 6th. That's it.
So you could say that the further to the right you go, x decreases and h increases.
Yes.
The further left you go, x increases
Mm-hmm.
and h decreases.
If you wanted to, you could actually visualize here that there is an h to the 0 here. Okay? And then over here, if you wanted to, you can imagine that there's an x to the 0. So when you start out, the power on x is 6, the power on h is 0, but then it goes 5, 1, 4, 2, 3, 3, 2, 4, 1, 5, 0, 6. Do y'all see they're just like switching? Sure. All right, so I went over here, Pascal's triangle, I did all this. What was it that I did this about? Why was I doing this? Because I was trying to figure out what x plus h to the n was, right? So let's see if we can't figure that out. What would x plus h to the n be? Well, you're not going to be able to tell me everything, but you're going to be able to tell me the things that are important. What's the first thing? X to the n, okay? plus, now, what's the number that would go here? N, right? Because remember, this is 6, comes from 6. 5 comes from 5. 4 comes from 4, right? So this is going to be n. And then tell me about the power on x. X to the what? One less, right? One less than this. But it's n, so I'm just going to have to write n minus 1. And then what about h? H. Agreed? Okay. Plus, now the next one, the number's going to be, I don't know, it's something off the triangle, right? But I claim we aren't even going to need it, all right? So I'm going to leave a blank here because I don't know what the number is. Tell me about the power on x. X to the what? N minus 2, and what's the power on h? H squared, right? Okay, what about the next one? Well, I don't really care about the number. Tell me about the power on x. N minus what? 3, and h what? Cubed. And then this is just going to keep going on, right? Until I get to the very end. And when I get to the very end, what is the last term out here? H to the n. Y'all agree with that? Okay. Let's go back now and take a look at that limit again. I need that line right there. I just had to convince you. If I just threw this up on the board, you'd be like, what the, right? If I just like said, oh, if I would have said that just a second ago, x plus h to the n becomes this, you would all be like, okay, whatever, right? Do you see where it comes from now? All right, here we go. There is a way that you can get these numbers without having to make Pascal's triangle, but I'm not going to show you that right now. All right, here's where we were. Limit, h goes to 0. We were at x plus h to the n minus x to the n all over h, right? And we were really hoping to cancel that h out. So now this becomes limit, h goes to 0, and now I'm going to rewrite this with the formula that I just showed you on the board. It was x to the n plus n times x to the n minus 1 times h plus something we didn't know, x to the n minus 2 times h squared plus something we didn't know, x to the n minus 3 h cubed plus a bunch of crap, and at the very end we had h to the n, right? That's this, right? Minus what? X to the n. All over what? All over h. Do y'all see it? What's going to happen here? The x to the n's are going to cancel. This and this cancel, right? Everything that's left has at least one h, doesn't it? This has an h in it, that has an h in it, that actually has two of them. That has an h, all of these have h's, right? So can I factor an h out? Yes. Let's do it. Limit. Starting to get goosebumps. I've been doing this for way too long and I still get excited about it. I don't know why. Guess I'll stop doing this when I'm not excited anymore. All right, so this right here, I'm pulling an h out, right? So I get n x to the n minus 1, right? Okay, and then this one plus, I didn't know what it was. It's x to the n minus 2, and I pulled one of those h's, so what's left? An h. Plus here, x to the n minus 3, I pulled one of those h's, so what's left? H squared plus dot, 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 very last one, h to the what? It's just one less than that, right? Because I pulled one h out of this. So if that was h to the, let's say h to the 100th power, this would be h to the 99th, wouldn't it? Y'all agree? Yes. And that's all that's left on top, right? All over h. And then the h's cancel. Okay, now take the limit, right? When h goes to 0, what happens to this? Nothing, right? There's no h here. What happens to this? Goes to 0 because it has an h, right? Gone. This one? H there. Gone. What about all these guys in here? They all have h's, right? They're all gone. Very last one? Gone. So the only thing left at the end of the day is that, which is the formula. Right? That's the formula. That's how you prove the power rule. It's not straightforward. You have to know some stuff first before you can do it. But it's pretty amazing, I think. So now you're allowed to use it, all right? So let's move. Well, should we do another example? Yeah, let's do one. Let's do an example using the power rule. If you're a math major, then hopefully that sort of thing gets you a little excited, because if it doesn't, you might want to rethink whether or not you want to be a math major. All right, let's do an example. Y is equal to 1 over the cube root of x. Find y prime. What's the derivative of that? Well, first of all, we are not going to use the limit, all right? We want to use the power rule or any of the shortcuts that we're learning today if we can. So the question is, can you rewrite that as x to a power? Yes. Okay, so first of all, what is this? This is 1 over x to what power? That's 1/3, right? That's 1/3 cube root of x. It's 1/3. Now I need to have this written as x to a power, not 1 over x to a power. So how can I write that? Yep, bring it upstairs. X to the negative 1/3. You see that? Now I have x to the n. What's n here for me? Negative 1/3, right? So I can use the formula. So the derivative of this is going to be, the negative 1/3 comes out, right? Negative 1/3 comes out. X to the, now be real careful here, you have to take the n, which is negative 1/3, and you have to subtract from it 1. So you have to get a common denominator there, right? 1/3 minus 1 is the same as negative 1/3 minus 3 over 3, which is the same as negative 4 over 3. So that's negative 4/3. Which is the same as negative 1 over 3x to the positive 4/3. If I drop it back down, right? Since this is a negative exponent, I can drop it back down to here, and it would join the 3. And then if I wanted to go even further, I could write that in radical notation as the cube root of x to the 4th. There we go.
Will we be done if we just left it 3x to
This one?
the one next to it?
I would say that if you're going to leave it and not simplify it, like not go to radical notation, if you're not going to do this, just leave it here.
Okay.
Because if you wanted to take the derivative again, then it already looks like x to the n.
Yes.
So you wouldn't have to bring it up again. Yes.
Can we do another one of these examples?
You want to do another one? If you want. We'll just do that. That one's not quite as hard. So what is that rewritten? You have to write it as a power of x. So that's x to what power? Negative 4?